Good morning, everyone. My name is Robert Blum with Intel. I'm really sorry that I couldn't join the session in person today, but I'm glad that the organizer. Good morning, everyone. My name is Robert Blum with Intel. I'm really sorry that I couldn't join the session in person today, but I'm glad that the organizers were able to allow me to submit a recording of my talk. I want to talk about high volume integrated silicon photonics for next generation LiDAR and other sensing applications. So as many of you are probably aware, Intel has quite a unique process in that we're able to integrate or combine indium phosphide with silicon in the same manufacturing process. And this gives us the ability to add gain for lasers or semiconductor optical amplifiers onto our silicon platform. And we do that by having this wafer bonding process where we put indium phosphide down only on those areas where we really need it on the silicon wafers. And then after the bonding process, we define through photolithography the laser structures and do the patterning at that point. We also don't have any exposed facets in the indium phosphide, which gives us a significantly improved reliability. And also we're able to, because we are fully functional lasers at that point, we're able to actually do wafer level burn-in and full wafer level testing of these chips as manufactured. So that not only helps with cost, but also it helps with overall reliability. So this is a quite powerful mature platform that we have been leveraging for several years now. One of our first products that we released based on this technology is shown on this slide. It's our 100 gig CWDM4 transceiver, which in fact we released to production here at ECOC 4 years ago, back in 2017. If you focus on the bottom half of the photograph here, you will see the Silicon Photonics transmitter chip, which integrates 4 lasers with a different wavelength on the CWDM4 grid, together with several monitoring photodiodes, the Alexander modulators for each of those channels. The modulators also integrate several monitoring photodiodes to control the quadrature bias points of these modulators. And we also have an optical multiplexer in a shell grading that is integrated on the same photonic chip. And you will notice that above the modulator, we have also integrated an electrical driver IC that is flip chip bonded on top of the Silicon Photonics die. So this has been quite a successful product for us. We don't not only ship it into data center applications, but also have qualified it for industrial temperature operations so that it can be deployed in 5G wireless fronthaul applications that have to operate from minus 40 degrees centigrade all the way to 85 degrees C. And because of the unique design where we don't have any exposed facet, we can benefit from the better heat sinking capabilities, thermal properties of the silicon. We really are seeing exceptional reliability and quality data from these modules. We have now shipped more than 5 million units into the field, and we're seeing laser failure rates of around 2 FIT, which is 2 failures per 1 billion device hours, and the module DPPM is around 30 for the entire CWDM4 module. And we're also shipping now 200 gig and 400 gig modules based on this same approach. And another example of the capability here is shown in this photonic chip, this 1.6 terabit capable photonic integrated circuit that was used for our demo of the co-packaged switch last year in March 2020. So this chip combines 32 lasers for 16 channels. So we have redundant lasers here, the 32 hybrid lasers. We have 2x1 selector switches, number 2 shown here, which can select either of 2 lasers should one laser fail. So we have redundant lasers here. We have 16 microring resonators, and then we have mode converters that allow us to output the light to the right through fiber V groups, right? So this is a little more complicated chip than the CWDM4 you've seen before, and it really shows the capabilities of this platform, where basically we have a fully integrated transmitter chip, and can really take advantage of integrating the indium phosphide onto the silicon as well. And the other thing that you will notice here is also that we have moved from Mach-Zehnder modulators to microring modulators, because they use much less space, and we were able to, despite the increased frequencies, we were really able to drive them at 106 gigabits per second using PAM4 modulation. So when we look at the various components that are possible in silicon photonics, we obviously have all the active components that I just talked about, lasers, SOAs. We can also do superluminescent LEDs. We can do silicon germanium photodetectors. We do the modulators in silicon. We have a whole suite of passive optical components such as muxes and demuxes, optical filters, splitters, and combiners. We can couple into free space. So we have couplers that go out at the edge, or we can also go out vertically with a 45-degree mirror, for example. We can also use grating couplers. We have standard interferometers or switches that are based on Mach-Zehnders or ring resonators, and we're able to control the polarization as well. And then we have a suite of electronic circuits and components. We choose to only integrate resistors and capacitors at the silicon wafer level, and have more flexibility by using discrete electrical circuits for functions such as the modulator driver, transimpedance amplifiers, the CDR or microcontrollers, and in particular SerDes, the high-speed SerDes, which need to be manufactured in the leading edge CMOS node typically. So by putting the electronic circuits outside the Silicon Photonics platform, we have the flexibility of really designing them in different processes and then packaging them all together into a tightly integrated chip. You see the chip here at the bottom right, which typically includes the silicon components. It has some resistors and capacitors integrated. And then the modulator driver, for example, will be flip chip bonded directly onto the silicon chip. So on this slide, you see a typical laser performance from our hybrid DFB lasers. On the top right, you see output power at 1310 as a function of drive current. And you can see several things. One is that we're able to actually get lasing all the way up to 100 degrees centigrade, which is quite impressive in my opinion. We're also able to get 10 milliwatt output power at 80 degrees C with 60 milliamps of drive current, and about 25 milliwatt of output power at with 100 milliamps of drive current. So these are very mature and well-performing, high-performing devices on our platform. And again, what is important here is that these lasers are fully uncooled and can operate really across a wide temperature range. And as an example here on the bottom left, we're showing you obviously the tight process control, where you see the clustering of the laser wavelength as manufactured, within plus or minus 1 nanometer, give or take, and the excellent RIN and SMSR at worst case operating conditions of 0 degrees C here for data center applications. And we're also have published data at lower temperatures, at minus 20 degrees chip temperature, for example, for other applications as well. So RIN less than 155 dB per hertz, and SMSR better than 40 dB across temperature and wavelength for these types of lasers. And as I mentioned earlier, we're able to obviously put different epitaxial materials down onto the same chip, or we are able to use the same one single piece of indium phosphide for multiple lasers. So for example, at the bottom left, you can see the LR4 product that we have. And there we use a single piece of indium phosphide because the wavelength spacing is only a few nanometers or 800 gigahertz to be precise between each wavelength. So we're able to have one piece of indium phosphide with 4 laser wavelength lasers manufactured below that piece. And really the wavelength control as manufactured is better than 0.3 nanometers if per 0.3 nanometers of standard deviation. On the right, this is some data for an 8 wavelength solution where we have lasers from 1270 nanometers all the way to 1410 nanometers as per the CWM8 MSA. There as well, what we did there is use 8 different pieces of indium phosphide, all put down on the same piece of silicon. So it's a single chip that has 8 lasers integrated. And then also we have the optical multiplexer integrated onto the same chip. And you see the passband for these different wavelengths superimposed onto the bottom right graph as well. Another key component besides the lasers are ring modulators or ring resonators. We have extensively validated those for 100 gig PAM4 applications. That was also part of that 1.6 terabit chip that I showed you earlier. We have now increased the capabilities of those modulators to 200 gigabits per second. So what you see here are some early results that we first talked about at OFC in June. You can see at the bottom left, we have quite a nice electro-optic response from these modulators with frequencies above 50 gigahertz, and both simulated and measured 200 gig PAM4 eyes on the right side. Interestingly enough, these microring modulators or resonators are also a key component for sensing applications because they're very sensitive to refractive index changes in the proximity of the PN junction, and so you can use them to detect changes in material that is, for example, on top of these resonators. I'm not showing you any data here. I'm just showing you the sensitivity in terms of the bias voltage and how the wavelength can shift, and obviously you can use that to measure changes as well with the right control or feedback loops as well. But overall, obviously, what is important for the high speed here is that we have very high phase efficiency and also very low resistance and capacitance, which enables us to go to these high speed, high bandwidth results that I've shown you in the previous slide. And Meir Sakib also talked about it yesterday at the show here. Another result that was just recently published is a slightly different design where we have added a germanium implant on top of those microring resonators, and the germanium really allows us to tune or trim those modulators at the wafer level to really get them all on the same resonant wavelength. And this is really a key capability that we think is necessary for a lot of these types of applications. So on the top right, you see the resonant frequency or the transmission spectrum across wavelength for a complete wafer across all reticles. And you see obviously that the resonant wavelength varies quite a lot across the wafer, from 1307 to 1313, and that after the trimming, which is done fully automated at the wafer level, fully automated without any intervention, we're able to bring all those resonators across the entire wafer to within plus or minus 32 picometers. And again, this is enabled through the germanium implant and through localized heating, which changes the profile of the implant. So if you want to read up more on that, there's an article in the Journal of Light Wave Technology, which was just published last month. Another component are germanium photodiodes. We use them for coherent receivers, for example. So here you're able to detect or keep the light in the waveguide and just detect it directly from the waveguide without having to couple it out of the waveguide. And here, again, we're showing you some frequency data where you can see that the bandwidth is well in excess of 30 gigahertz for these types of devices. So this is a device that's not necessarily needed for some of the transceiver applications that we're shipping today, but it's really a key component for some of those next generation components. So I promised I would talk about LiDAR, and so let me do that now. One of the questions is, why do you need LiDAR? Why can't you just do self-driving with cameras alone? And the answer is, you can. You can have fully automated vehicles that are driving and making decisions based on cameras alone. But for truly self-driving, if you think of level 4 or level 5 levels where you really take your eyes off and don't pay any attention, you take your mind off and don't really look at the road. For these types of application, you really require exceptionally high mean time between failures or between safety critical events. And to do that, and also to get people's confidence, you really need to have two independent subsystems that are both fully hands-free capable. And the goal is really, by having these two independent subsystems, you're then able to get really two capabilities that are orders of magnitude better in performance and driving performance, and then safety critical errors than human drivers. And so the approach that Mobileye, an Intel company, is taking here is that there is a what is called a supervision ADAS camera subsystem that is by itself capable of hands-free driving. And then on top of that, they're developing, or Intel is developing, an independent radar LiDAR subsystem that is also in and of itself able to drive fully hands-free, so without any cameras. So you just use imaging radar, high-resolution radar, and LiDARs for front-facing to get you to the MTBF levels that are really required for level 4 or for level 5 automated driving. And so if you look at the capabilities that are needed for this, really it's a lot of it has to do with moving from today's generation time of flight LiDARs to FMCW or coherent LiDARs. And coherent LiDARs have several advantages. For once, with them you're able to detect not just distance of an object, but also velocity, and instantaneous velocity is the important term here. So you can just put one point on a target, and you're able to instantly infer or measure the velocity of the target. You also get significantly improved detection range. Time-of-flight LiDARs typically are able to measure up to 200 meters in ideal conditions, and part of that has to do with the 1/r squared decay and signal. But for FMCW, because it's a coherent LiDAR, you can get a significantly larger range, 300 meters or more, due to the 1/r decay. And also you are much less sensitive, if not immune, to interference from other targets, again, because you're using coherent detection. So really the goal here is to develop a system that measures around 2 million points per second with very high resolution, with many points on the target. And so to do that in Silicon Photonics, we need a few more things that I haven't talked about yet. One is obviously, because we're going into free space, we want to be able to do so with high output power. And one of the key building blocks for that is, again, our indium phosphide, which enables us to do not just lasers, but also optical amplifiers on chip, right? And the principle here is very similar to a laser, except that if you look at the bottom left, now what you do is you take an optical mode, you pull it up into the indium phosphide where you amplify it, and then you have another taper that brings it down into the waveguiding layer, but now with significantly higher output power. And on the graph on the right, you see the gain as a function of output power. And if you focus on the red curve, which is our nominal operating current, you see that we're able to achieve 20 dBm or 100 milliwatts of output power with 10 dB of gain, which basically means 10 milliwatts in gives us 100 milliwatts of output power out of the chip. Or similarly, if you look at the 17 dBm output power, which is 50 milliwatts, we have 25 dB of gain. So much less, significantly less than one milliwatt can be boosted to more than 50 milliwatts of output power. So this is a very powerful component because we now can put multiple SOAs. We can put dozens of SOAs onto the same chip and really get multiple channels to output light for these types of free space applications. Other components that are critical for this, for coherent in general, are polarization splitters and rotators, so PSRs, and also polarization insensitive input and output couplers. So this is some data that, again, Mayor Saqib is showing here at that conference. The paper is shown below, but we're able to achieve around 20 dB of polarization extinction ratio. And the top left shows you how this is measured. Again, this is something that we can measure at the wafer level, so it's really easy to optimize these types of components because we're able to get measurements really quickly. And then also at the bottom right, I'm showing you the input-output of these couplers because we're going into free space. We have a taper, we go into free space, and what is important there is that you really have good uniform performance across the wavelength range for both TE and TM polarization, which is shown here. So we're quite significantly below 0.3 dB of loss per facet here across the operating wavelength range. And then finally, you want to have really good beam quality as you go out of the chip, really across multiple channels, right? And so this is shown here, where we see a nice Gaussian distribution. Really, for those of you who are in the optics field, one of the measures is obviously the m² value, which here we're able to achieve better than 1.2 for these output couplers. So these are all edge couplers where the light is emitted from the edge of the Silicon Photonics chip. And so when you put it all together, you really get to a point where you have more than 6,000 active and passive components, and that's really counting waveguide bands and tapers all together. But you can integrate all these components onto a single chip, and Mobileye talked about that quite extensively at CES early this year. So I've put a few links down below if you're interested to read up more of that. But it's a really compact chip that enables you to really have well over 100 lines, scanning lines across the field of view. And it's a very powerful tool with dozens of SOAs integrated on the same chip here. So in summary, if we look at Silicon Photonics overall for sensing application, what is really critical here is that we have this mature high volume platform now. In fact, we're shipping at the industry's highest volumes in Silicon Photonics with industry leading quality and reliability. I talked about our ability to test and burn in at the wafer level. And really that gives us the ability to go through fast development cycles as well, because we don't have to wait for singulation of the die and then packaging to get test results. We're able to measure directly at the wafer level, run the design of experiments, get the data, and feed it back to the designers so we can really turn designs quickly. We have on-chip gain, obviously, as I talked about a lot. but not just for lasers, but also for SOAs. And again, it's a mature, proven platform on the laser. We're able to do multiple wavelengths, different wavelengths on the same chip, and we're able to manufacture SOAs with up to 100 milliwatts of output power out of the chip. We're developing FMCW LiDAR applications. Really, the high volume deployments in consumer AVs are going to be in the 2025 timeframe. But these coherent LiDARs are really an ideal application for silicon photonics. But there are many other sensing applications that can take advantage of the components that we have developed on the Intel platform. I talked about the trimmable microring resonators, but we also have obviously the multi-wavelength lasers and tunable lasers. We have waveguide photodiodes, different types of modulators, edge couplers, and just an array of passive components. So it's a really powerful platform. And if you're interested more about the capabilities of the platform, then please reach out to me. So with that, I want to thank you again, and I apologize I'm not able to take in-person questions, but please do feel free to email me at robert.blum@intel.com. Thank you again.